Welcome to AI Frontiers, a podcast exploring the latest advances in artificial intelligence research. Today we'll be examining the multi-agent revolution, synthesizing 49 papers published on May 22, 2025. This collection of cutting-edge papers represents the forefront of AI innovation, collectively painting a fascinating picture of where the field is heading. These works highlight both remarkable breakthroughs and persistent challenges in artificial intelligence. As we journey through this research landscape, we'll uncover emerging themes, analyze groundbreaking findings, and consider what these developments mean for the future of AI. Let's begin our exploration of how researchers are pushing the boundaries of what AI systems can accomplish. Let's start with an overview of today's presentation. We'll be taking a journey through emerging AI research themes and breakthroughs that are defining the cutting edge of artificial intelligence. A key focus will be examining the significant shift from single models to collaborative multi-agent systems that's transforming how AI problems are approached. We'll explore how artificial intelligence is revolutionizing scientific discovery and education through new methodologies and frameworks. The presentation will investigate advances in reasoning capabilities, uncertainty quantification, and human-AI collaboration that are expanding AI's potential applications. Finally, we'll consider the broader implications of these developments for the future trajectory of artificial intelligence research and implementation. Artificial intelligence in 2025 represents a field in rapid evolution, extending far beyond its earlier limitations. AI research now spans a comprehensive range of capabilities, including reasoning, learning, perception, and even creativity. There's been a notable shift in how AI systems are conceptualized, moving from viewing them as mere tools toward understanding them as collaborative partners or autonomous agents that can work alongside humans to solve complex problems. Large language models have been particularly influential, demonstrating remarkable capabilities in natural language understanding, generation, reasoning, and specialized domain knowledge. The field has become increasingly interdisciplinary, drawing on insights from cognitive science, psychology, neuroscience, philosophy, and ethics. This cross-pollination enriches AI development and helps ensure systems are designed to be beneficial, safe, and aligned with human values and needs. The first major research theme emerging from these papers is the rise of multi-agent systems and collaborative AI. We're witnessing a significant shift from single-model approaches to distributed intelligence frameworks where multiple AI agents collaborate to solve complex problems. Yi and colleagues introduce XMAS, an innovative paradigm for heterogeneous large language model-driven multi-agent systems. This approach leverages diverse models for different agents, demonstrating significant performance improvements over traditional homogeneous systems. Similarly, Li and collaborators present the Know the Ropes framework, which strategically decomposes complex tasks into subtasks handled by specialized agents. Their approach shows remarkable accuracy improvements on algorithmic problems like the Nazca problem. These heterogeneous systems have demonstrated performance improvements of up to 47% on complex tasks. This theme reflects a growing recognition that complex real-world problems often require diverse capabilities that a single AI model cannot provide, mirroring how human teams with complementary specialized skills often outperform individuals working alone. The second prominent research theme focuses on AI for scientific discovery, with systems functioning as scientific collaborators or fully autonomous researchers. The NovelSeek Team introduces a closed-loop multi-agent framework for autonomous scientific research that operates across various fields. The system demonstrates significant performance improvements in tasks like reaction yield prediction and enhancer activity prediction, with dramatically reduced time costs compared to human efforts. In a similar vein, Bazgir and colleagues have developed causal large language model agents specifically for biomedical research. These agents can integrate multimodal data and perform intervention-based reasoning to infer cause and effect relationships in complex biological systems. This research direction highlights the potential for AI to accelerate scientific discovery by generating hypotheses, designing experiments, analyzing results, and iterating on findings. All with minimal human interventions. These systems could significantly reduce the time and resources required for scientific breakthroughs, while potentially uncovering insights that might elude human researchers. The third research theme centers on advanced reasoning capabilities, particularly long context understanding and selective thinking. Kim and colleagues introduce Infinity Thor, a framework designed for long-horizon embodied reasoning tasks that tests agents' ability to maintain coherence across hundreds of environment steps. Wang and team propose an innovative think-or-not selective reasoning approach for vision language models. This method enables AI systems to decide when detailed reasoning is necessary and when it can be skipped, mimicking human-like thinking processes. Their approach achieves a remarkable 90% reduction in computation without any performance loss through strategic allocation of reasoning resources. In contrast, Keysberg and colleagues reveal a dramatic gap between human and AI spatial reasoning capabilities. Their research shows that while humans achieved near-perfect accuracy on spatial pathfinding tasks, even the most advanced AI systems struggled significantly. These advances are enabling AI to maintain coherence and goal-directedness across changing environments, a crucial capability for applications like robotics and autonomous vehicles. The fourth research theme examines AI for education, focusing on pedagogical agents and visualization tools. G and colleagues introduce EduVisBench and EduVisAgent, a benchmark and multi-agent framework specifically designed for pedagogical visualization. Their system significantly outperforms baselines in creating educationally aligned visual explanations, achieving a 40.2% improvement over previous approaches. What makes this research particularly valuable is its focus on explanations that are not only correct, but also structured to support learning and conceptual understanding. These systems recognize the unique requirements of educational applications, where explanations must be tailored to enhance comprehension and retention. This research direction reflects growing interest in how AI can enhance learning experiences through personalized instruction, clear explanations, and visualizations that illuminate complex concepts. Such educational AI systems have significant potential to democratize access to high-quality personalized educational resources across diverse learning environments. Looking across all the papers, several key findings stand out as particularly groundbreaking. First, Ye and colleagues demonstrate that heterogeneous multi-agent systems substantially outperform homogeneous ones, showing up to 47% improvement on the AMI dataset. This challenges the conventional approach of using a single model type for all agents in a multi-agent system. Second, Li and colleagues show that strategic task decomposition enables smaller models to solve complex problems effectively. Their Know the Ropes framework enabled 3GP-40-MINI agents to raise accuracy on the knapsack problem, from just 3% zero-shot to 95% after patching a single bottleneck agent. Third, the NovelSeek Team demonstrates that autonomous scientific research can achieve practical success across multiple domains, with significant performance gains and dramatically reduced timeframes compared to human efforts. Fourth, Wang and colleagues show that selective reasoning can reduce computational requirements by 90% without sacrificing performance, enabling more efficient AI deployment. Finally, Keysberg and team reveal a significant gap between human and AI spatial reasoning capabilities, highlighting a specific cognitive domains where even advanced AI systems still fall far short of human performance. Examining the methodological approaches across these papers reveals several common techniques driving AI research forward. Multi-agent frameworks with specialized roles appear frequently, with systems like EduVisAgent, NovelSeek, and XMass all employing agents that focus on specific tasks or functions. This approach allows for modular system design, where components can be optimized independently. Reinforcement learning for reasoning improvement is another common methodology, with researchers like Wang and Sun using various reinforcement techniques to enhance reasoning capabilities of large language models. Systematic benchmarking and evaluation frameworks such as AgentIF, EduVisBench, and XMassBench enable rigorous assessment of model capabilities and facilitate progress tracking. Many researchers are employing hybrid approaches that combine neural and symbolic methods, leveraging the complementary strengths of different computational paradigms. Finally, autonomous exploration and knowledge mining techniques enable AI systems to learn from their environment without explicit supervision, as seen in approaches like GUI Explorer and High Entropy State, seeking for reinforcement learning. Let's examine our first seminal paper in depth. XMass. Multi-Agent Systems with Heterogeneous LLMs by Yi and colleagues. This work challenges the conventional wisdom of using a single large language model type for all agents within a multi-agent system. The authors demonstrate significant performance improvements when different models are strategically assigned to different roles based on their unique strengths. In a chatbot-only multi-agent scenario, their heterogeneous configuration yielded an 8.4% performance improvement on the math dataset. Even more impressively, in a mixed chatbot reasoner scenario, the heterogeneous approach achieved a remarkable 47% performance boost on the AIM dataset. The paper introduces XMass Bench, a comprehensive evaluation framework for assessing model performance across different domains and functions in multi-agent systems. This research was selected as seminal for its paradigm-shifting approach to multi-agent system architecture, suggesting that the future of complex AI systems may lie in heterogeneous configurations rather than scaling up single model types. Our second seminal paper is the NovelSeek Team's work on an autonomous scientific research framework. This closed-loop multi-agent system demonstrates the potential for AI to conduct meaningful scientific research with minimal human intervention. The system achieved impressive performance gains across multiple scientific domains while dramatically reducing the time required. For instance, in reaction yield prediction, their system increased performance from 27.6% to 35.4% in just 12 hours. In enhancer activity prediction, accuracy rose from 0.52 to 0.79, with only 4 hours of processing. And in 2D semantic segmentation, precision advanced from 78.8% to 81% in nearly 30 hours. These results are particularly notable because they suggest we're approaching an era where AI agents can function as genuine scientific collaborators rather than mere analytical tools. The paper was selected as seminal for proving that AI systems can autonomously conduct meaningful scientific research, potentially accelerating the pace of discovery across multiple fields and enabling researchers to explore more hypotheses than would be possible through traditional methods alone. The third seminal paper we'll examine is Know the Ropes: Strategic Task Decomposition for Complex Problems by Li and colleagues. This research demonstrates how algorithm-aware decomposition plus targeted augmentation can enable modest-sized models to solve complex problems without requiring ever larger monolithic models. The author's approach converts domain priors into algorithmic blueprint hierarchies for strategic task decomposition among specialized agents. In their experiments, 3GP Task 40-MINI agents achieved 95% accuracy on the knapsack problem, compared to just 3% in zero-shot attempts. Even more impressively, a 6-agent system reached 100% accuracy on the task assignment problems up to size 10 and 84% on larger instances, compared to just 11% zero-shot. This paper was selected as seminal because it challenges the prevailing assumption that solving increasingly complex problems requires ever larger models. Instead, it suggests that strategic decomposition and targeted enhancement of specific components can enable systems of smaller models to achieve impressive performance on complex tasks, potentially leading to more efficient, interpretable, and maintainable AI systems. Looking toward future directions, several clear research paths are emerging from these papers. First, developing more sophisticated coordination mechanisms for multi-agent systems will be crucial as these architectures become more common and complex. Researchers will need to address how diverse agents can most effectively communicate and collaborate. Second, bridging the gap in spatial reasoning and other human-like cognitive capabilities remains a significant challenge, as highlighted by the stark performance differences in spatial tasks. Third, creating more efficient uncertainty quantification methods for high-stakes applications will be essential for deploying AI in critical domains like healthcare and autonomous transportation. Fourth, designing ethical frameworks for AI thought partnerships and human-AI collaboration will become increasingly important as AI systems take on more collaborative roles. Finally, scaling autonomous scientific discovery to accelerate breakthroughs in critical domains like climate science, drug discovery, and materials research represents a promising direction with potentially enormous societal benefits. It's worth noting how this presentation itself was created, as it represents an example of AI synthesis and review. The content was synthesized using Anthropic's CLAUDE 3-7-SONNET-2D2502219, a large language model designed for comprehensive text analysis and generation. Text-to-speech synthesis was performed using DeepGram's advanced TTS technology to create natural-sounding narration. Visual elements and diagrams accompanying this presentation were generated using Grok's image generation capabilities. While all synthesized content was thoroughly reviewed by human experts for accuracy and coherence, it's important to acknowledge that some oversights may exist despite careful verification. All references to original research papers have been provided to enable listeners to explore the primary sources directly. This meta-analysis demonstrates how AI tools can be used to synthesize and communicate complex research findings while maintaining scientific accuracy. Subscribe to AI Frontiers to stay updated on the latest AI research developments. Our YouTube channel provides weekly research syntheses covering breakthrough papers across all AI disciplines. We offer comprehensive coverage of emerging trends and methodologies, with in-depth analysis of their implications for both research and practical applications. Expert commentary helps contextualize new findings within the broader AI landscape. Join our growing community of AI researchers, practitioners, and enthusiasts to stay at the forefront of this rapidly evolving field. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.